Hi, I'm Luke Craig.
And I'm Andrew Fasano.
And I'm Tiemoko Ballo.
We're researchers at MIT Lincoln Laboratory, and today we'll be talking about PyPanda. PyPanda is an extension of Panda, so it can be helpful to get some background on Panda itself. Panda is short for the Platform for Architecture-Neutral Dynamic Analysis. Panda is open source and developed by MIT Lincoln Laboratory, NYU, and Northeastern University. Panda is a fork of QEMU, which has been modified to enable whole system record and replay, callback structure at various points of interest during execution, a plugin-based architecture, which does analysis on callbacks. Panda has a large plugin library. Some notable plugins include a whole system taint tracking plugin, operating system introspection plugins, and syscall analysis. When we started designing PyPanda, we set out several goals. Top of mind was performance. We knew it would always be slower than a C-shared object, but that slowdown had to be manageable. Our next goal was unified analysis. Traditionally, with Panda, you might start up a live system, load it up with a binary or something you want to analyze, use the QEMU monitor to start a recording, type in command, stop the recording, and then do analysis on that recording. That process is difficult to reproduce exactly, and it segments the process into prep and recording commands, and then also the analysis on that. With PyPanda, we wanted to unify that process so it could all exist under the same script. Another goal of ours was facilitation of integration. It was paramount that our tool allow and enable easy integration with other tools. Access to core emulator structures is also very important to us. It was important that we present Python a true interface to Panda, which includes access to core structures, the ability to change them easily, while also giving the user advantages of Python objects like tab complete on various structures like a translation block. Lastly, we wanted to make the tool as easy to use as could be expected. With these goals in mind, we worked towards our first component, Panda as a library. Panda is traditionally built into an executable for each architecture target. We modified Panda to support targeting a shared object, which included adding the Panda API. The Panda API enables external scripting languages to do things such as start or stop an execution or a recording or a replay. It also exposes core functionalities such as reading virtual memory. PyPanda has several core parts. First, a Python module, which uses CFFI to act as a translation layer between Python code and C code. Second, libpanda, which is the C library component we discussed before. Third, we built a system for generating header files, which CFFI and therefore PyC parser can consume, so it has structure and function definitions. We unfortunately don't have time to get into that here, but there are details in the paper. To explain how to use PyPanda, we're going to introduce the Panda Lifecycle and run through an example. PyPanda has three running task contexts: a main Python thread, which starts up the other tasks, a core Panda task, which is multi-threaded and executes the CPU, and a guest driver, which enables us to queue interactions with the underlying machine. We begin with our Panda constructor. After importing our module, we initialize Panda three ways for three different architectures, depending on the argument. Our first initialization on line 9 is an i386 generic image. A generic image is a sample image we make available. This initialization starts a QCOW downloading if it doesn't exist on the machine, which has a snapshot at a root command line, as well as OSI profiles already enabled. Generic images exist for many architectures. Our second and third initializations show how you can use PyPanda with arguments you might be more familiar with in QEMU. In these examples, we use a custom QCOW in the first and a development kernel in the second. Next up in our example, we'd like to do analysis of a custom program. We use our guest driver thread to queue a guest driving action. This is in the same script as the rest of the example and what we refer to as unified analysis. In this example, we revert to a snapshot, copy a directory containing our program to the guest, or start a recording, run our binary that we copied through the command line, end the recording, and then request that the CPU exit. Next, we'd like to do some analysis on our program, which we do with callbacks. Our first callback on line 1 is a before block execute callback. This callback executes each time Panda executes a basic block. In this function, we wait until we get to address hex 1234, print a message, and then disable our callback. Our next two examples are plugin to plugin callbacks. That is, they are callbacks received from a running plugin. In the callback on line 8, we use the hooks plugin to receive a callback when the address is hex 1234. This is functionally the same logic as the callback on line 1, but is much faster because we check the address for each basic block in C. In this way, we can get the best of both worlds by performing more basic logic in C for speed and more complicated logic in Python. Our second plugin to plugin callback on line 13 is a callback registered with the syscalls2 plugin, which triggers when the guest executes the syswrite syscall. On line 16, it uses our operating system introspection capabilities to read the process name. It then reads the buffer that the process is writing from virtual memory. And lastly, it prints out that buffer that it read. All we need to do now to complete our lifecycle is start up our execution. We can load any C plugins we'd like to run at the same time. In this case, that's acid story with custom arguments. We can then either run the guest normally or run a previously made recording. When our guest finishes execution, the thread returns to Python and runs on line 10.
Now, for the rest of this talk, we're going to be looking at analyses that you can build on top of PyPanda. To start, I'll walk us through developing a simple analysis right now. At the start of our script, we're going to import the Panda class from the Panda RE package. We request a generic 64-bit x86 guest. This will automatically fetch a pre-built QCOW virtual machine that is pre-configured for Panda analyses. In particular, this means that the virtual machine has a terminal exposed over a serial interface, that it has a snapshot called root that was taken after the guest booted and somebody logged in, and that Panda's operating system's internals plugin has a configuration for this kernel. Now, you can create your own images, but if you just want to do a simple analysis, we have these generic images available for you. So first, let's consider how we want to drive the guest's execution. We use the panda.queueBlocking decorator to label this function as a function that should be run in PyPanda's blocking thread and automatically queue it up to run after the guest starts. This needs to run in a separate thread from our analyses, as these commands will block while waiting for the guest VM to respond to the commands we've typed into it. We begin this function by asking Panda to synchronously revert the guest to the root snapshot where it's booted and logged in, that snapshot I mentioned a moment ago. Then, once that revert finishes, we're going to type some commands into the terminal and get the responses and print them. When these commands have finished, we'll tell PyPanda to end the Panda execution and any analysis that has been enabled. We can actually run this for now with no analyses set up. First, the script is downloading that pre-built generic image I mentioned. It takes a moment. And now it's running our commands and printing the output. But this is pretty boring, so let's actually set up an analysis to observe the behavior of the guest while it's running and tell us some information. Panda provides over 40 core callbacks and 60 plugins which provide even more callbacks. And we certainly don't have the time, and we probably don't have the patience to go into all of those. So for now, let's just use one of my favorites, the syscalls plugin, which provides callbacks whenever the guest enters or returns from any given system call. Using this decorator, we'll register a function to be called whenever the read system call is about to return. Our function gets a handle to the emulator's CPU state, current program counter, as well as all the arguments passed into the system call. We can grab the process name using a PyPanda helper function. Under the hood, this uses the OSI plugin to determine information about the currently running process. We can also access this plugin and call its functions directly from PyPanda. There are sharper edges here, though. This function returns a CFFI object representing a C structure instead of a simple string, but we can still grab the name field from that structure and convert it to a Python string with just a little more code. Similarly, we can directly query the system calls plugin to get the return value of this system call in an architecture agnostic way. With this read syscall, that's going to be the number of bytes that have been read into the caller provided buffer argument. Then we can directly read that buffer out of guest memory and print it along with the name of the process that issued the system call. Now, this is just a simple example of what you can do with PyPanda. We're only using two plugins, a single callback, and we're analyzing a live system instead of a recording. But as you can see on the right side of the screen, our analysis worked. We collected all the information we wanted, and we did it in just 30 lines of Python code. Now, for our paper, we conducted 3 case studies where we built more complex analyses on top of PyPanda. Let's turn to these now. All 3 of these case studies, as well as the example I just demonstrated, are available at the following GitHub link.
Another case study we built with PyPanda was creating a dynamic heap monitoring system. The goal of this was to record memory allocation and freeze by processes in user space as well as the kernel. The workflow for this was fairly straightforward. First, we need to locate the free and allocation functions in the guest libc and kernel. For the kernel functions, we register hooks at the addresses of those functions and record the memory being freed or allocated. For user space processes, we need to set up callbacks that will run whenever a process may have loaded libc, and then if it has just loaded libc, we set up hooks for each individual process such that we can run our analysis on each heap allocation or free. So the first thing we're going to do is we're going to run some commands in the guest to get some information out of it. So we begin on line 125 by reverting the guest to a snapshot where it's already booted and we're logged in. Then, as shown in the code on lines 129 through 131, we run a couple of standard Linux commands in the guest. We use the find command to locate the libc shared object on disk, and then we use a combination of nm, grep, and awk to find the offsets into libc for the malloc and free functions. Next up, we want to find the addresses of a couple of kernel functions related to heap allocations. So we grep again through the file system.map to find the address of kfree, kmalloc, and vmalloc. Once we have these addresses, to start we're going to set a hook using the decorator panda.hook at the address of kfree. This is shown in lines 140 through 142. When kfree is called, our Python function will run. We'll grab the value in rax, which is the address of the buffer being freed, and we'll record that using a little helper function remalloc. Now, for the other functions that are doing allocations, it's a little more complicated. We need a hook to run at the time when the function is called, such that we can grab the size being requested, but then we also need some more information at the time the function returns. So we're going to implement that through a helper function, hookret with args, and what that function is going to do is call the argument function we're providing on line 145 here with both the input args as well as the return value of this function. This is just a simple anonymous function that grabs that information and calls another helper, addAlloc. So let's dive into that first helper function, hookret with args. Again, we're using the @panda.hook decorator, and we set up a hook to run first _enter at the address provided. When this hook runs, we grab the return address by reading an integer off the top of the stack, and we grab the first 2 arguments passed to the function. This assumes a standard calling convention for the given architecture. Now, within that function, at the time that the guest has begun executing the function we want to hook, we set up a second hook, _return. The first thing we do when this hook is triggered is we disable it because we only want to run it once. We grab the return value from the function, and then we call the user provided function, which as we just saw previously was a lambda function, and we call that using the arguments we grabbed as well as the return value. Now these are the 2 helper functions that are actually storing information about active allocations. It's just a simple Python dictionary where we insert and delete elements. After we've set up our hooks on these kernel functions, we need to also set up hooks for each user space process. So we do this by checking at a number of different times to see if a process has libc loaded, and if so, we register those hooks. The times we're making this check is whenever there's a task change, whenever the system call break returns, and whenever the system call mmap returns. In these three cases, we call the add hooks if necessary function. Now, in this helper function, all we're doing is checking if libc has been loaded into the current process. If it is, we grab its base address and we add the offsets for malloc and free that we previously found in the first step. Once we have those addresses, we know exactly where in this process malloc and free are, so we set up hooks. Again, for the free function, we set up a simple hook on lines 61 through 65 where we just call the remalloc function. And on lines 55 and 56, we set up a hook ret with args, again using that previous helper function. So we can hook when we enter malloc and get its return value as well as its input arguments. And that's pretty much all there is to it. In under 200 lines of Python code, we've created a system to dynamically track heap allocations and frees over time.
In this use case, we are going to be comparing intermediate representations, or IRs, for binary analysis. Now, a comparison is of interest because we rely on IRs for a range of reverse engineering and program analysis tasks, and because PyPanda lets us leverage any IR with Python bindings, so an analyst is free to choose the best tool for the job. The IRs under test are Vex, Pcode, and BAP. Though we use the latest Python bindings for each, unfortunately, that does not mean we can test a modern version of BAP. How are we doing the testing? So our methodology, which we call dynamic oracle testing, uses faithful whole system emulation of a real binary as a source of both realistic non-random input, because we lift the instruction byte stream, and ground truth for any analysis conclusions, because we're able to observe concrete execution events. Let's walk through what this process looks like in the context of call graph reconstruction. So first, we read the bytes encoding every basic block executed in the guest right after that block executes. So here we have a notional basic block, and we see that it contains a call instruction. Now that call is a relative offset call whose destination would be the program counter 1337. We feed each of these blocks into all three IRs simultaneously, and we use the APIs of each IR to find direct and indirect calls and returns within every block. Now it's at the time that the next basic block executes, which will be the call destination if a call is found, that we check the correctness of our IR-based predictions. By repeating steps 1 through 3 for the duration of the execution of a specific binary, we're able to aggregate the following totals. First, we have the number of direct call true positives, which is when the IR correctly found a call and computed the correct destination. Then we have the number of indirect calls found by an IR. Now, we don't count these against the IR since a static analysis cannot know the call destination. Next, we have the number of returns found, which would be important for rebuilding a call stack or reconstructing a call graph. And finally, we tally the number of failures, which is when the IR throws an exception during lifting or produces no IR statements. Now, we know that block is a valid one because it executed within the guest. So what did we find in our dynamic oracle testing case study? Well, firstly, we can say that Vex is the most accurate and robust of the three IRs for call graph reconstruction, particularly in user space performance. Now, Pcode does have a slight edge in kernel space because it supports certain privileged instructions, sysexit on x86 being one example, that are not handled by the other IRs. Now, if we step away from accuracy and consider speed, we note that Vex and Pcode are comparably fast, while BAP is a bit slower and a bit more variable. Now, this isn't necessarily a property of the IR itself, rather the implementation of the Python bindings. In BAP's case, we make remote procedure calls to an OCaml server. So the takeaway here is that PyPanda allows both rapid integration of analyst-chosen binary analysis IRs and evaluation against a dynamic ground truth.
Malware authors often pack their binaries for obfuscation and to increase the difficulty in statically reversing them. Userland dynamic analysis can work, but malware authors regularly employ techniques to check for tracing and either exit early or not unpack at all. We can use PyPanda to take a recording of a packed binary and do analysis on that recording. This is a better approach because analysis done at the hypervisor level is harder to detect. Packed binaries have higher entropy as their data is typically compressed or encrypted. We can tell when a binary is unpacked into memory as the overall entropy of the program will decrease. We would like to build a tool to combine this knowledge and make static reversing of packed binaries easier. In our example, we take a recording and measure the entropy when execution is in a given process throughout the recording. We graph entropy against time and allow the user to make a selection. In our example below, a user might pick something after the entropy has settled at 30 million instructions, or compare it to something at 28 million instructions to see how the unpacker generally works. After a selection has been made, we read all of memory and transfer it directly into a running Ghidra instance. We begin by starting two processes with Python's multiprocessing library. They use a shared memory manager to access two shared arrays. Our PyPanda process gets a callback on every basic block and calculates the entropy of our program after every n blocks. It adds the entropy to our shared array. The Flask web server serves a web page that is dynamically updated over async IO with values. When a user clicks a point, Flask starts up another process. This process loads up our original replay in PyPanda, waits until it reaches the clicked point, and uses Ghidra bridge to transfer state to Ghidra. Now I'd like to show off our demo for our human-in-the-loop unpacker. We start in our published Docker container in the unpacker directory. We've made a recording called bash with our make recording script. We record our PyUnpacker with our recording as an argument and set our granularity to every 10,000 basic blocks so that we can take a measurement of entropy every 10,000 basic blocks. Next, we switch to our web server run with Flask, where our values for entropy will appear once the program has shown up. You can see various points on here, close to 7 entropy. You can see here the entropy going down over time, which you'd expect for a packed binary. Next, we select a value that looks interesting to us. This one looks good to me. Switch back over to here, and we'll see our recording running. And once it reaches the point that we've selected, it will show things on screen with it reading operating system introspection information to read the entirety of the virtual memory mapping. Here it is. You can see the mapping here. And we can switch back over to Ghidra, and you can see it populating that here. Once it has finished populating, it will automatically set our cursor to the program counter at the point that we've selected and run the auto analysis in Ghidra. You see how it's changed here? This is the point, this is the program counter that we have. You'll see Ghidra's decompilation engine and its auto analysis starting to get to work. With just a few hundred lines of Python, we've linked together PyPanda, Flask, and Ghidra. In summary, PyPanda meets our design goals. Its consistent 1 to 2 times slowdown from core Panda was well within our tolerance. Its unified analysis provides a reproducible way to produce recordings and do analysis in the same script. Our implementation enabled simple integrations, including Ghidra via Ghidra bridge, as well as Flask, PyPcode, PyVex, and BAP. PyPanda scripts have full access to core emulator structures and can use them as though they were Python objects. PyPanda is relatively easy to use and has features such as generic images to make up the startup process much easier. As we proceed to develop PyPanda, we plan to release frequent updates through PyPy and continue to improve performance. If you'd like more information on PyPanda, you can visit panda.re or pull our Docker container.